Good morning. This is Physical Chemistry, Part 1, Thermodynamics, Chapter 1, Fundamental Concepts. Section 1.1, What is thermodynamics and why is it useful? Thermodynamics studies the behaviors of matter and transformations of energy on a macroscopic scale. So, matters include gases, liquids, and solids. Transformations of energy include the conversion between potential energy and kinetic energy, or conversion from one form of potential energy to another form. What does macroscopic scale mean? Let's compare macroscopic and microscopic side by side. So first, the number of atoms. On the left-hand side, we're talking about moles of atoms or molecules. On the right-hand side, microscopic is referring to one or few atoms or molecules. When we are looking at macroscopic properties, the units are bigger. For example, kilogram, meter, kilojoule. Microscopic, we're talking about individual atoms or molecules. So we're talking about atomic mass unit. That's 1 gram per mole. Or it's 1 kilogram divided by 10 to the power 3 and then divided by 6 times 10 to the power 23. That's the Avogadro number. When we're talking about length on the microscopic level, we use angstroms, nanometers. This is angstrom. 1 angstrom is 10 to the power negative 10 meters. When we are talking about energy, usually it's around 10 to the power of negative 20 plus minus 5 joule. When we are talking about macroscopic properties, it's the average properties of moles of atoms and molecules. A mole is a huge number. 1 mole is roughly 0.6 trillion. For example, if we're talking about the pressure of 1 mole helium gas, that's actually the pressure exerted by 0.6 trillion helium atoms to a surface. What about microscopic properties? Again, they're referring to just one or few atoms. If we're still talking about pressure, we can look at the collision between 1 helium atom and the surface, and then somehow statistically look at the average behavior. And then we will be able to obtain the macroscopic property. What about energy? Energy is the ability to do work. Energy can be potential energy or kinetic energy. There are only 2 categories. It's either potential energy or kinetic energy. So what's the difference between these two? Potential energy depends on the relative positions of the objects. Kinetic energy depends on the relative motions of the objects. Let me give you a few examples. So first, potential energy depends on the relative positions. Gravitational energy. If you raise an apple, you increases its potential energy. Attraction, repulsion energy between opposite or like charges. Think of a H2 molecule. The 2 hydrogen nuclei repel each other. The 2 electrons attract the 2 nuclei, while the 2 electrons repel each other. And then bond energy, that depends on the internuclear distance. For example, again, H2. If you stretch or compress the bond between the 2 hydrogen atoms, the potential energy changes. The kinetic energy depends on the relative motions of the objects. For example, translational energy, rotational energy, and vibrational energy. I'm about to show you this translation, rotation, and vibration motions of a water molecule. So over here you see a water molecule. Now I'm going to have this water molecule doing translation upward, downward, left, right. This is translation. And then we can do rotation about this axis that passes through the oxygen atom. So we're going to do this rotation. All right, so this is a rotation. We can also rotate the molecule about two other axes. Why is this? Okay, I cannot show you the third one because the third one is perpendicular to my computer screen over here. All right, that's the third one. But I can certainly show you the rotation about this axis. All right, we just need to be a little careful. All right, that's one for rotation, another one. All right, and then how about vibration? I'm going to show you the vibration as well. Let me show you the so-called asymmetric stretching. This is asymmetric stretching of the two OH bonds. Now what about symmetric stretching? So this is the symmetric stretching. The third one has a lower wave number. That's the bending motion. The bond angle changes. All right, so let's get back to the three categories inside this kinetic energy: translation, rotation, vibration. But actually, when we are talking about vibration energy, it includes both kinetic and potential energy. Why is that? Let me show you another example. If you look at the spring, when it oscillates, the kinetic energy and potential energy are transferred to each other, are converted to each other constantly. When it's fully stretched or fully compressed, the kinetic energy of these two objects is exactly zero. And when this spring returns back to the equilibrium length or equilibrium position, the potential energy becomes zero. However, during the entire process of stretching and compression, the total energy of the spring must be conserved. Therefore, we are looking at the conversion between the kinetic energy and potential energy of this spring and of course these two objects.